In this video, we will discuss the end behavior of a polynomial function. Our whole goal is to eventually be able to graph a polynomial function. So in the last video, we talked about the leading coefficient and the degree, and we'll tie that in as we discuss end behavior in just a few moments. Before we get into graphing polynomial functions, we're going to look at a specific class of functions called power functions, because those are honestly the simplest types of polynomial functions when the exponent is a certain number. A power function is a function of the form p of x is equal to a times x to the n, where a and n are real numbers. In this video, we will explicitly look at where we have n being an even or odd whole number, and we'll look at the value of a being either 1 or -1. We will first look at the case where n is an odd whole number, such as 1, 3, and 5. I have already graphed the functions y equals x, y equals x cubed, and y equals x to the 5th. And I just want you to look at these graphs and just notice some general characteristics from this. Notice that y equals x is that basic identity function. It goes through the origin, has a slope of 1. Notice also that the graph behaves differently as we go to the ends of the x-axis. As x gets larger and as x goes to infinity, notice that the graph to the right is going up. As x gets smaller and goes to negative infinity, the graph is going down. Y equals x cubed behaves in a similar fashion. As we go to the right, the graph goes up, and as we move to the left, the graph goes down. And also y equals x to the 5th, as we move to the right, the graph goes up, and as we move to the left, the graph goes down. We call this the end behavior. These graphs are all down to the left and up to the right. These graphs also have a common x and y intercept, that is at the origin, but notice as the exponent gets larger, the graph gets a little bit flatter through the intercept, and the graph also gets steeper as we increase the exponent. So we can state those facts here. The graph gets flatter through the intercept and vertically steeper as the exponent increases. The domain and range of these functions is all real numbers. And the end behavior that we were just describing as x goes to infinity, that is, as we go to the right side of the graph, the y values were going up, so we write that as y goes to infinity. And as x goes to negative infinity, that means the left side of the graph, we notice that the y values were going down, right? The graph is going down there, so we say y is going to negative infinity. Now if we consider these same graphs, except now the coefficient is a -1, that is, we have y equals negative x cubed, and negative x to the 5th. These graphs are simply reflections across the x-axis of the previous graphs. The domain of these functions is still all real numbers. But notice that the end behavior of these graphs changed. Now, as we go to the left, the graph is going up. As we go to the right, the graph goes down. And that is the case for all of these odd degree polynomial functions whose coefficient is a -1. The leading coefficient is negative there. In this case, we say then that as x goes to infinity, so as we go to the right side of the graph, the graph is going down, so we said that y goes to negative infinity. And as x goes to negative infinity, that is the left side of the graph goes up. So we say y goes to positive infinity. Now let's examine these power functions, again, special cases where the exponent is an even whole number. And the first case is where the coefficient is just 1. So we'll look at y equals x squared, y equals x to the 4th, y equals x to the 6th. And you could graph these by hand. All you would have to do is plug in values 1, 2, and so on. We have seen the graph of y equals squared quite often. Y equals x to the 4th, you can imagine the numbers are going to get much larger, much quicker. But notice that the behavior of these graphs all looks very similar, right? It's just getting very much like we saw with the odd powers. The graphs are getting flatter through the intercepts, and the graphs are getting vertically steeper as the exponent increases. The domain is all real numbers, so we'll write negative infinity to infinity. And the range going from bottom up is from 0 to infinity. As far as the end behavior, notice that as we move to the right end of each of these graphs, what's happening? Yeah, the graph is going up, so that means the y values are increasing. So as we go to infinity, y also goes to infinity. And as we go to negative infinity in the x direction, so as we move to the left side of the graph, what's happening? The graph is going up. So that's saying that y goes to positive infinity. In fact, notice that on the left side and the right side, they're both going up. So I like to say this a lot of times, that for odd, we just saw the graph went in opposite directions, but for even, the graph is going to go in equal directions. And when we examine the negative x squared, negative x to the 4th, and negative x to the 6th, you should notice again that these graphs are just reflections across the x-axis of those previous graphs. The domain is still all real numbers. And the range, this time from bottom to top, is negative infinity to 0 with a bracket. As far as the end behavior, as we move to the right side of the graph, that is, as x gets larger and larger, notice that the graph is going down. And so we write that as y approaches negative infinity. And as x goes to negative infinity, that is on the left side of the graph, the graph is going down. And so similarly, we say y is going to negative infinity. So the end behavior here, when we have an even degree but a negative leading coefficient, the graph goes down to the left and to the right. So let's just review those cases here. So when we have an odd degree basic polynomial function, it goes down to the left and up to the right. And when we had the odd degree but a negative coefficient, it went up to the left and down to the right. An even degree with a positive 1 coefficient went up to the left and up to the right. And a negative coefficient with an even degree went down to the left and down to the right. This in part leads to something we call the end behavior test. And it states that the graphs of the basic polynomial functions and their reflections enable us to graph any polynomial function. The end behavior of the graph of a polynomial function, p of x equals a sub n x to the m plus all the way to a sub 1x plus a sub 0 as x approaches infinity or as x approaches negative infinity resembles a graph of that basic power function p of x equals a sub n x to the n. So knowing this end behavior of those basic power functions will get us the general shape of the graph of a more complicated polynomial function. We'll summarize what we just talked about. This table will describe the end behavior of a polynomial function based on the parity of its degree, that is it even or odd, and the sign of its leading coefficient. So if n is odd and a sub n is positive, what I like to think about in that case is either the graph of y is equal to x or x cubed. If you can get that basic shape in your mind, then that tells you that to the left the graph goes down and to the right the graph goes up. So as x goes to negative infinity, y goes to negative infinity, and as x goes to infinity, y goes to infinity. If we have an odd degree with a negative leading coefficient, again think of negative x or negative x cubed, then the graph will go up to the left. So we say that as x goes to negative infinity, y goes to infinity. And the graph goes down to the right. As x goes to infinity, y goes to negative infinity. So you're thinking about those basic shapes to help you there. If n is even and we have a positive leading coefficient, think about y equals x squared, then the graph will go up to the left and up to the right. So as x goes to negative infinity, y will go to infinity. As x goes to infinity, y goes to infinity. If we have an even degree with a negative leading coefficient, think of y equals negative x squared. The graph goes down to the left and down to the right. So as x goes to positive or negative infinity, y goes to negative infinity. So an odd parity, the end behavior will be opposite on the two ends. An even parity means that you have equal end behaviors on the ends of the graph. And here I have an actual visual to help you kind of just see that. So an odd degree, positive leading coefficient. What we're going to find is that for these more complicated polynomial functions, it's going to do something crazy in the middle, but at the end it's going to behave like that y equals x or y equals x cubed, that basic power function. For a negative leading coefficient, I show you the opposite effect, right? The reflection will take place. And then likewise for an even degree with a positive leading coefficient and negative leading coefficient, the ends will either be both up or both down depending on the sign of the coefficient. For this particular slide, I want us to determine the end behavior of each function by first stating the degree and leading coefficient, and then we'll match it with the graph that it has to correspond to. I've given you 4 different functions that I've graphed on the calculator, but really just wanting you to think about right now the end behavior and how the coefficient and degree will imply what end behavior the graph has. The first one is negative 5x cubed plus x squared plus 3x minus 4. This function is in standard form. We have a negative leading coefficient, right, the negative 5. And the degree is 3, which is an odd degree. So a negative leading coefficient, an odd degree, think about the negative x cubed, that basic graph is going to come up to the left and down to the right. We'll match it in just a minute. 7x to the 6th minus x to the 5th plus 8x cubed minus 8x plus 3 is our next example. In this case, we have a positive 7 as our leading coefficient, so we have a positive leading coefficient. The degree is 6, which is an even degree. So an even with positive, I need you to think about x squared, and that's going to go up in both the left and right directions. The next example is negative 4x to the 4th minus 13x cubed minus 8x squared minus 1. This polynomial has a negative 4 leading coefficient, so it has a negative leading coefficient. The degree is 4, which is even. So when we think about like negative x squared, it goes down to the left and down to the right. The last polynomial is 3x to the 5th minus x squared minus 8x plus 5. So its degree is 5, which is odd. The leading coefficient is 3, which is a positive number. So if you think about the graph of x or x cubed, notice that it goes down to the left and up to the right. So when we match these functions to their correct graph, the end behavior can tell us exactly which function it has to be. The first one went up to the left and down to the right, and the only one that does that is this third graph. Our second function went up to the left and up to the right, so the only one that has that is this first graph. Then we had a negative leading coefficient with an even degree, which is both down, and that's going to be this last graph, because notice that the end behavior, again, I don't care what happens in the middle, I'm looking at the extreme ends of it. They both are down. And so now we have the last example, which was down to the left and up to the right, which is this second graph that I have here. So this example is to determine the end behavior of each polynomial function. We have a polynomial p of x equals negative 2x to the 4 plus 3x squared minus 7x plus 5. This is in standard form. We know that we have a negative 2 as a leading coefficient, so we have a negative leading coefficient. The degree is 4, which is an even number. So a negative leading coefficient with an even degree, think about the graph of negative x squared, it's going to be down to the left and down to the right. Or we could also state that in arrow notation, that as x goes to positive infinity, y goes to negative infinity. And as x goes to negative infinity, that is to the left, y goes to negative infinity. So as x goes to infinity, we're saying as x is going to the right, as we go to the right side of the graph goes down, which is to negative infinity. Part B is p of x equals 3x cubed times 2 minus x squared times x plus 1 squared. To find the sign of the leading coefficient and its degree, we need to multiply the leading terms of each of these factors. In the 2 minus x, the leading term is negative x, but we square it. We're going to get a positive x squared. in the x plus 1 squared. The leading term is x, but when we square it, we get an x squared. Multiplying these leading terms of each of the factors together, 3x cubed times x squared is 3x to the, 3, 4, 5, 6, 7. So this has a positive leading coefficient and an odd degree. So again, think about y is equal to x or x cubed to know that it's got to go down to the left and up to the right. So we say as x goes to infinity, y goes to infinity, right? That's saying as we go to the right, the graph is going up. And as x goes to negative infinity, the graph goes down, right down to the left, so y goes to negative infinity.